Now finally, we can look at integrating e to the x, which has a very simple formula. Since the derivative of e to the x is e to the x, the antiderivative of e to the x is e to the x. Let's try an example here with integrating x squared e to the x cubed. Notice that x cubed is in the exponent, so if we were to substitute this, its derivative would be 3x squared, so we would have a multiple of the x squared factor that we see here. So for this integral, we'll start by letting u equal to x cubed. Then du will be 3x squared dx. And so this x squared can be replaced with 1/3 du. So our integral transforms into 1/3 e to the u du, which will be 1/3 e to the u plus c. And now we can put our u back in, which was x cubed. So we have 1/3 e to the x cubed plus c. Suppose I want to find the area under the curve y equals e to the negative 3x from 0 to 1. In this case, e to the negative 3x, we can imagine, would be this exponential decay graph. So from 0 to 1, we're looking at the area of this region here. So we'll integrate, find the area from 0 to 1, e to the negative 3x dx. Well, in this case, we've got e to the negative 3x, which at some point we can perhaps do this mentally, but let's just work this out by hand. If I let u equal to e to the negative 3x, then we get the constant negative 3 as its derivative. And so I'll have a negative 1/3 comes out with the substitution. Since negative 1/3 du equals dx. Oh, sorry, that should be dx. I can also change the limits of integration. So for instance, when x is 0, we get u equals 0. So 3 times 0 stays 0. And when x is 1, we get u equals negative 3. So my new limits of integration will go from 0 to negative 3. Of course, the integral will now be evaluated with respect to the variable u. So we'll integrate from 0 to negative 3. And evaluating this, we'll have e to the negative 3 minus e to the 0. So that leaves me with negative 1/3 e to the negative 3 minus 1.